Okay, this week we're going to move into wind and weather. Mainly we're going to talk about wind. Wind is basically just motion of the air. You feel it when you walk outside. So we need to understand what forces make this to happen. What forces control speed and direction of the wind. One of the interesting things up until now, we've only talked about quantities that are scalar. In other words, they are just one-dimensional. Wind speed is multidimensional. It's a vector. It has both speed and direction. In other words, if I defined the wind and told you it was 25 miles per hour and didn't tell you where it was coming from, it might be a little bit interesting, but it would sure be nice to know where that wind came from. So we need to know both parts. We need to know where the wind's moving from and what the speed is. So wind basically has two components. So it's basically just the local motion of the air. And we apply Newton's second law of motion, force equals mass times acceleration. So if there's an acceleration of an object, it's going to create a force. And guess what? Wind is actually a force too, because you think about it, the damage it can do with building and stuff if it's strong. But there are forces that work to make wind. There's air pressure gradients. There's centripetal forces. There's Coriolis effect, friction, gravity. All of those work together to create the wind we see. So here's just a quick look at isobars. That's a pressure gradient force. The pressure gradient in this case would go from high pressure towards low pressure, because the pressure gradient is always going to try to get rid of low pressure. So in that case, you can see they're fairly tight. So there's a pretty strong force between here and here. Basically, it's how close the isobars are to each other on the map. Here they're a little further apart. The pressure gradient is still going that way. And the pressure gradient is perpendicular to an isobar. It literally goes like that. So if that's the only force, then the wind would always be right across an isobar. But there's others. Centripetal force. Around low pressures or high pressures, winds go in a circle, don't they? We talked about it. We have counterclockwise around low pressure, and clockwise around high pressure. So there's another force, the centripetal force or center-seeking force. I don't know, if you ever drive a car and go around a corner, you ever wonder what holds you on that road instead of flying out off that corner? It's centripetal force. It's not independent. So in other words, if you get rid of that force, that object will just take off on a straight line, because you're back to Newton's first law of motion. An object moving in a straight line remains so, unless acted on other force. But if it's curved, like when you're going around a curve in the car, and if you're allowed to take that corner, there must be a centripetal force holding you there. There's another force called Coriolis force. It arises because the Earth rotates. Take a look at this drawing. We know the Earth rotates. Sun comes up over here, sets over here. So the Earth is moving like this. So if it's moving, we know the top isn't moving nearly as fast. After all, 24 hours, the equator is going to go all the way around. And the pole has not much to move there. So you can see in a short amount of time what's happened. We wind up with a tilted looking, and there's a force acting to the right of everything here because of the Coriolis force. So the fact that our Earth rotates, the Coriolis force is in effect. And guess what? It's stronger up here than it is at the equator, where it actually goes to zero. So the strongest Coriolis force is the further north you get, or the further south you get. And it basically deflects the wind to the right. So if you have winds that's blowing from the south due to a pressure gradient force, they're going to turn to the right due to the Coriolis force. Friction. You ever watch the wind go across the ocean? It blows fairly steadily, not much friction there. As it hits land, it slows down, and there's a whole lot more friction. So when the wind hits the land, it becomes rougher. Maybe there's mountain ranges. All of that slows down the wind, and that's friction. So now we're going to combine all these forces also with gravity. Gravity is just a force that acts downward. Does not apply to horizontal winds, but it will apply to vertical winds. So first thing we're going to talk about is combining forces, the hydrostatic equilibrium. What the heck is that? Well, think about how fast air pressure decreases in the vertical. Remember, we said that you can go up to about 5,000 feet, and roughly that is 850 millibars. So in 5,000 feet, you dropped 150 millibars. That's a heck of a pressure gradient in the vertical. But guess what? Nothing moves that way, does it? Air doesn't leave the earth, doesn't go out flying into space because it's accelerating up because of that pressure gradient. It hits pretty steady. So with that, that's because gravity holds it there. And that pressure gradient force is balanced by gravity so that air parcels tend to just hang there if they're not acted on by some other force. So you wind up with a parcel of air just hanging out, basically, due to gravity and the pressure gradient force. So the pressure gradient force is much greater in the vertical than it is in the horizontal. Here's another wind, geostrophic wind. It's a combination of pressure gradient force and the Coriolis effect. It causes the wind to go parallel to isobars, or in this case, contours even. Because as the more and more the Coriolis force keeps acting on the pressure gradient, on that wind particle, it turns it more and more to the right until the Coriolis force and the pressure gradient force are balanced. There we go with going around the centripetal force, around high pressure. You can see the wind tends to go outward, but the centripetal force holds it coming back in, making it go in a curve. Coriolis force will also have an impact on that wind as well. So the Coriolis force and the centripetal force will combine for that. That's the gradient wind. And low pressure is just the same thing. Friction. Friction slows the wind. So it changes both Coriolis force because it's slowing the wind down and the speed the wind flows. What it does is cause winds to blow inward toward low pressure and outward away from high pressure. That's basically what the friction does. So you can see in the low, the pressure winds are going to curve inward towards the center of that low. There is a continuity. If you have winds, our air is all connected, both in the horizontal and vertical. So say you have horizontal divergence at the surface. You're probably going to have air sinking to take its place. It doesn't get a vacuum there. So if the air is sinking from above, there's probably horizontal convergence that's taking place aloft. So you wind up with air flowing downwards. In the middle of a high pressure system, a lot of time, almost always you're going to have convergence aloft, sinking motion, and horizontal divergence. Remember the pressure gradient. The winds are flowing outward in the high because of friction. And the opposite occurs during the low pressure system. We talk about continuity as well over a surface. Remember if wind's blowing from the water to the land. Well, it hits the land, friction is a whole lot more. So it slows down when it hits land and it starts to rise. So when you go upwards then, it pushes the air up and you wind up with clouds. The same thing holds if you had very strong winds coming from the land and all of a sudden they pick up over the water. Well, if they do, and you get faster, what happens? You get divergence, winds blowing downward, you clear out. In the future chapters here, we're going to start talking about planetary scales and synoptic scales, mesoscales. All different scales of winds are defined in one of these 4 categories, basically. And we're going to move into those starting in the weeks ahead. So with that, let's just take a quick peek at some weather. I wanted to show you on a surface weather map. Look at the winds. There's low pressure over Kansas right now, eastern Kansas. Winds are rotating inward towards the center. High pressure over here, winds are rotating outward, away from the high pressure. So, centripetal force, all of those forces, we're actually verifying it in real time on a weather map. If you go to 700 millibars and look at a contour, here is a geostrophic wind. Notice how they're almost always right parallel to the, in this case, contours, but which are similar to isobars. And you can see the tighter the gradient, the stronger the wind. The less the gradient, the less the wind. So, again, it corresponds very well with what you've been learning about. In order to show you somewhat of the continuity of wind, divergence is occurring right in this area over Kansas. Guess what? If you have divergence aloft, we have rising motion. Rising motion means we have lower pressure at the surface. Lower pressure at the surface means we're getting convergence there. And where's the low pressure? Kind of over that area of Kansas. So that divergence aloft corresponds pretty well with that convergence at the surface. And you can actually see it right here in rotation with Kansas and with the low there, pulling up moisture into it. So everything works together, and that's how the winds go. And they're all, what happens at the surface is related to what happens aloft. So understanding the forces literally in 3 dimensions is what a meteorologist is trying to do. So if you have any questions about this, please don't hesitate to ask.